Example 15 demonstrates edge detection on satellite images using the Sobel filter. This example is the raster library to read dim data and SciPy library for the Sobel filter. Firstly, you will define the path to the dim data file, then open the dim file and read the data. After that, create a dictionary to save figures if it doesn't exist. Then apply the Sobel filter for edge detection. Then check the min and max values of edges for debugging. After that, plot the edge detection result using a different color map. The output is edge detection on dim data of AirBell govern rate. Example 16, LSTM model for time series prediction. You will explore how to build and train an LST model for time series prediction. We will demonstrate this with two applications, accreted data and real prediction, asynthetic sense wave data, and real precipitation data for the AirBell govern rate from 81 to 2020. First, let's generate some data. We create a sense wave with 1000 data points, which we reshape into a column vector. We use a time series generator to prepare the data for our LSTM model. We set the input length to 10, meaning the model will use the previous 10 time steps to predict the next time step. We then define the LSTM model with one LSTM layer of 50 units and a dense output layer. We compile the model with the Adam optimizer and mean square error loss function and train it for 10 epochs. After training, we make predictions by iterating over the time series data using the model to predict the next value based on the previous 10 time steps. We calculated the mean absolute error, MAE, to evaluate the model's performance and plot the predictions alongside the actual data. The result of MAE is very low. Now, let's move on to the second application, predicting annual precipitation data for AirBell govern rate. We start by loading precipitation data and normalizing it using a min-max scaler. We again use a time series generator with an input length of 10. This time, we define a more complex LSTM model with two LSTM layers, 150 units, and drop out layers for regularization. We compile the model with the Adam optimizer and MSE loss function and train it for 200 epochs. We then make predictions on the scaled precipitation data and inverse transform the predictions back to the original scale. To evaluate the model, we computed several accuracy metrics, MAE, MSE, root mean squared error, and R squared. Finally, we plotted the predictions against the actual data, showing the model's performance over the years. The result of R squared is 0.67, and the figure represents time series of both predictions and actual precipitation data of airwell governorate.